Hello everyone. Today we are going to continue discussing the arithmetic operations, the advanced arithmetic operations in AVR microcontrollers. So last class we covered the parts of the unsigned numbers. So we discussed the unsigned number data, how to make addition, subtraction, multiplication, and the division. And today we are going to take care of the unsigned data. So this was the unsigned data we discussed last class, the addition, subtraction, the different subtraction, the multiplication, and we figured out that there is no division instructions in AVR. Okay, however, there are some division instructions in different microcontrollers, but again, for the RISC or reduced instruction set code of AVR, we don't have such instructions, so we can do division as we discussed in the previous class, like this code. So we are going to simulate division by means of subtraction. Now, let's start discussing today the signed data. How can we operate or make signed data, and how can we add it, subtract, and so on. So let's figure out what the meaning of signed data. So unsigned, we discussed the last class. Unsigned is 8-bit data, since we have 8-bit microcontroller. So all of data should be 8 bits. So all of the 8 bits of the byte are used to represent the data or the number. However, what about unsigned? What about signed data? Let's figure this out together. So for signed data, you know, in everywhere life, numbers are used that could be positive or negative. All of time, guys, we need to represent numbers in positive or negative. For instance, in our applications in electrical engineering, we have sinusoidal AC supply. So the sinusoidal AC supply needs positive and negative numbers to be represented. So this is one example of our life. All of sensors, all of the machines need positive and negative data. For example, also temperature. So a temperature of 5 degrees below 0 can be represented as -5, and 20 degrees can be represented as +20. So in this case, guys, we need to present data in positive and negative. So we need signed data. How can we represent this signed data in AVR? So the signed data are arranged in a computer as follows. So this is not only for AVR, but this is generally for computers. So the most significant bit, MSB, which is the last bit in the left-hand side for the 8-bit microcontroller, this is nothing but D7. So the most significant bit is set aside for the sign, positive or negative. So in this case, guys, this means the signed data are going to be represented in 8-bit microcontroller in only 7 bits from D0 to D6. So D is referring to data. So data can be stored from D0 up to D6, which means now the number is 1/2 of the 8-bit. So you know that 8-bit is 256 number, or from 0 to 255. However, in this case, since we are going to exclude the last bit from our data, so we have only 2 to power 7, not 2 to power 8, which means now the data is 128, or the number is 128, which can be represented from 0 to 127. So this means the maximum data that we can represent in 8-bit microcontroller in case of signed data would be only 127. So it can be either plus 127 or minus 127. So this means we have a range of data now from minus 127 up to plus 127. So this is the range of data that we can represent in the 8-bit microcontroller. Now, again, the bit number 8, which is D7, can represent the sign. So how can we represent the sign now? If it is active high, sorry, if it is active high, so this is going to refer to negative sign. If it is active low, so the number would be positive. So again, if D7 is 0, so this means it's positive number. And if D7 is 1, so this means we have negative number. So this is now just to represent the data now. So we said from D0 to D6 we have data, which can vary now from 0 to 127. And the last bit is our sign. So again, the range of data that we can represent now in 8-bit microcontroller is vary from the most negative number, which is minus 128, okay, to 127. Sorry, it should be minus 128. So from minus 128 up to plus 127. How? Because we have what's called tooth complement. So we'll see how the tooth complement can represent 128, not 7 only. Okay, so we have from minus 128 to 127. So let's correct this here. Okay, so this is here from minus 128 to plus 127. Okay, let's see how can we make negative number. So negative numbers, for negative number, as we said, D7 would represent all of time the sign, okay? So negative number D7 will be 1, okay? However, the magnitude is represented in the 2's complement. Last class we discussed the meaning of 2's complement. We will elaborate more today what about the 2's complement, how we can calculate it, okay? So again, the value or the magnitude is not represented as data as it is. It should be 2's complement, which means if you have data, like let's go to the previous slide, here, if you have this number, you cannot say now this is negative 0. For instance, you have here the first number here, this number here. You cannot say that this is negative because this is 1, and you have 0 here. So we cannot say this is 0. So this is already a number. However, how we can get the value? You should get the real number because this is now 2's complement. It's not the number itself. Okay. And again, here, for instance, this is minus and this is 1. So it means the value now is not minus 1. How can we get it? You should use the 2's complement to get the real value of this number. So again here, guys, although so the magnitude is going to be represented by the 2's complement, and we will see how to calculate the 2's complement of any number. One more note is, although the assembler does the conversion, it's still important to understand how the conversion works. All of time, guys, our concept in this course is to understand the mechanism of microcontroller, the mechanism of computing, not only the results what we can see. So how can we figure this out? Let's investigate together. So to convert to a negative number, representation of 2's complement, follow the following steps. First, write the magnitude of number in 8-bit binary without signs. Then invert each bit. So make complement for each bit. The 1 should be complemented to 0, and 0 should be complemented to 1. After that, add 1 to your results. So 3 steps now. First, write the binary of your number, okay? Second, invert each bit or complement each bit. Third, add 1 to this number. Let's see some examples here. How can we get the 2's complement of numbers? For instance, here, this example required to show how the AVR would represent the -5 number. So in order to represent -5, so firstly, write the binary representation of this number without sign, which means 5. So 5 is nothing but 1, 0, 1, 0, and the second nibble is 0. So this is now 5. Second step is make complement for all of this. So 1 would be 0, 0 will be 1, 1 will be 0, and 0 will be 1, and then all of these will be converted to 1. So this is our inverted number. Add 1 to this number, so 0 plus 1 would be 1. Then all of the number will be resulted here like that. So this is now our tooth complement. If you have a look, this number, if you consider this number as unsigned number, this would be F, and this part would be B, because 1 plus 2 plus 8. So this is B. So now the -5 can be represented as FB. However, how can we figure out in our arithmetic or calculations if the number is going to be negative or positive? This is very important. So we will elaborate more in this class. How can we figure out if the number is positive or negative? Okay, because as you can see, this number now can represent -5 and at the same time can represent plus FB, which means it's confusing for us now. How can we figure out if this number is positive or negative? So there will be some indications. How can we figure out if the number is positive or negative? So we can say here -5 equals in hexadecimal FB hexadecimal, and the sign number representation in tooth complement for -5. So again, guys, when you see a negative number in microcontroller, you cannot figure out the data. You have to bring the equivalent tooth complement in order to get the real value of this number. Okay. So since here, guys, we have D7, which is last bit in our number, this bit is active high, so this means now it's negative, and this value need to be figured out by tooth complement in order to represent the real magnitude of this number. Okay, let's see another example. We would like to represent -34. So how AVR is representing this number? So again, 34, first nibble is 4, second nibble is 3. So 4 is nothing but 0, 0, 1, 0, and 3 is 1, 1, 0, 0. Firstly, make complement. So each 0 will be converted to 1, and each one will be converted to 0. And then add 1. So when you add 1 here, so 1, let's write it here, plus 1. So 1 plus 1 equal 0, and carry is 1. Again, 1 plus 1 equals 0, and the carry is 1. So we have 1 here. 1 plus 0 plus 1, 1 plus 0 equals 1. So we don't have carry here. 1 plus 1 equal, sorry guys, sorry, we add only 1. Again, sorry, 0 plus 1, sorry, we add 1. 1 plus 1 equals 0. Let's write it outside here, do not be confused. So 1, 1, 0, 1, 0, 0, 1, 1. We need to add 1. 1 means all others would be 0 like that. So 1 plus 1 equals 0, and the carry is 1. 1 plus 1 equals again 0, and the carry is 1, and we don't have anything here, so this would be 1, and remainder will be the same. So this would be our tooth complement okay, which is representing minus 34. Again, if you find this value in hexadecimal, the equivalent decimal would be 8 plus 4, which is C, and here 8 plus 4 again, so this is C. So this number could be positive CC or negative 34. Why it could be negative? Because the last bit here, D7, is active high. Again, how can we figure out? We will see later how can we figure out. But we have here one comment which is going to give us indication for the negative sign. So let's read the comment of this example. Therefore, minus 34 equals CC hexadecimal. The signed number representation in tooth complement for 34H. The D7, which is the last bit, equals N. What is N? N is the negative flag in the status register. So this is the first thing that we can understand if our number is positive or negative. So if N equals 1, so this means the number is negative. So N equals 1, and all of time N would be the result of D7 of our register. Okay, guys, so this represents here or indicates that the number here is negative. Okay, nice. Let's see another example here, minus 128. So 128 can be represented as you can see here. So 0, 0, 0, 0, 0, 0, 0, 1. So this is the 128. When we convert the number, it would be 1, 1, 1, 1, 1, 1, 1, 0, like that. And now let's add 1. So when we add 1, it would be converted again to 1, 0, 0, 0, 0, 0, 0, 0, which means it become like 80 in hexadecimal. Why this is 128, by the way? You know 127 is represented by FF. So 128 equals 127 plus 1, which means you need to add 1 plus FF. So FF plus 1 equals 1, 0, 0, like that. Okay, so this is our representation of 8 bits. 127 is FF plus 1, this would be 100. Okay, so here this is a numerical problem because this is not 128 now, this is representing 80, not 128. Okay, so here we have some typo here, guys, in this example, because 1000, this number now is represent 80, not 128. So this number is not like that, it should be 80. Okay, so this is here 80. Okay, because 128 is 100 in hexadecimal. Okay, so again, in order to represent this number, so we have here 1 and all of these bits are zeros, so this is the representation of 80. And now in order to get the tooth complement, we should make complement of all of that. Okay, and then adding 1, so adding 1, it would be again 80. It will be the same, but this time is negative sign. So this is 80 hexadecimal, okay, and it is the same as a positive representation. So here, guys, sorry, instead of writing 128, this would be 80, not 128. So this is minus 80. Okay, nice. So again, guys, here the high bit, so the high bit, it was already active high, or most significant bit was already active high, okay, which is D7. So for the number here we have this number, so the one here is active high, either for the number or the tooth complement, which means which one is positive and which one is negative. Now it's still confusing. So how can we figure out if the number is positive and negative? Is n sufficient to figure out this? Actually not, because we said n would be the same as D7 for each number. And D7 here is already active high, either in positive or negative. So how can we figure out the difference between positive and negative? So n is not sufficient to figure out this this problem. How can we figure this out? Let's observe that from another status register pin or flag. The AVR indicates the existence of an error by raising the V overflow flag, but it's up to the programmer to take care of the erroneous result. So what's the meaning of that? AVR indicates the existence of an error by raising V. So V would be raised sometimes, okay, but this is going to be wrong. How can it happen? Let's see that in examples together. The CPU understands only zeros and ones and ignore the human conversion of positive and negative numbers. So finally, the processor or computer would read zeros or ones. The computer will not figure out the difference between positive and negative. However, he only needs to have zeros or ones, and we can change the mechanism in order to make negative sign. If the result of an operation on signed numbers is too large for the register, an overflow has occurred and the programmer must be noticed. In order to figure out the meaning of these expressions, let's solve the first example here. So examine the following code and analyze the results, including the N and V flags. So we need to figure out what happened to N, negative flag, and V, which is overflow flag. So let's see this program together, guys. We have here LDI R20, LDI R20 with a value of 60. So here R20 would be 60 hexadecimal. When you represent 60 hexadecimal, so this is 0. This is here 2 plus 4, so this is 6, which is in decimal value, it's 70. And when you convert 60 to decimal, it will be 70. From hexadecimal to decimal. And adding 46 in the register R21. So this would be now 46, this is 6, and this is 4, which is in decimal plus 96. So as you can see, both of numbers now are positive numbers. If we make add operation now for the two registers, the result would be added in R20. So we can say R20 equals 96 plus 70. When you represent this in decimal number, the result would be like that. Let's make it here. 0 plus 0 equals 0. 0 plus 1 equals 1. 0 plus 1 equals 1. 0 plus 0 equals 0. Here again, 0, 1. 1 plus 1 equals 0, and we carry 1 here, so the result here would be 1. So this is our result of addition of these two numbers. Now, if you would like to see the value, here, due to having D7 equals 1, so this means the N flag would be active high. Why? Because D7 equals 1. and the other value would represent the tooth complement. So, which means now it's going to be minus 90. But this is completely wrong. This is not the right answer. How can we figure out that? So let's see together what will happen to the number. So when you make the addition, you will find n1 equals, or n equals 1, this is negative, and v also equals 1. Why v equals 1? Let's see here. According to the CPU, the result is negative, when which is wrong. The CPU sets v equals 1 to indicate the overflow error. So we have overflow error. For this overflow error, it's going to make active high like that. So n would be 1, and v also would be active high because of the overflow, to indicate the overflow error. Remember that n flag is D7 if n equals 0, so the sum is positive, and if n equals 1, so this is negative. So what we could see here, guys, that n would be made active high. However, it's still positive number. So we still have the same problem. We still have the same problem. How can we figure out? So even here, n and v are not sufficient. So let's see here how we can solve this operation, and we will see another sign, another flag, which is S, which will solve all of the problems of signed number. So in 8-bit signed number, v is set to 1. The v, or overflow, is set to 1 if either of the following two conditions occurs. First condition, if d6 to d7 but no carry out of d7, so this means at c equals 0, or the other one, if there is a carry from d7 out, which means carry equals 1. So the overflow, guys, is not only for the overall 8 bits now. The overflow is for bit number 7, or d6. So let's go to the previous example here. Here, because the summation of d6 is overflow, which means 1 plus 1 is 0, and we have carry here. So here, since we have overflow for d6, the v flag is active high. So this is a reason. So again, the v flag will be active high in one of the following two conditions, not both of them together, just one of them, which is either d6 to d7 is overflow, which is similar to our previous example. So at d6, there was 1 plus 1, and 1 plus 1, this means we have overflow now. So the result would be 0, and there would be 1 bit carry on d7. The carry flag here is still 0, because carry flag would only appear if d7 is overflow, not d6. But here, the v flag would appear either d6 to d7, but in this case, carry flag should be 0, or d7, okay, which means c equals 1, but no carry from d6 to d7, which means one of them, guys. It cannot have overflow for both of d6 and d7, just one of them. So here, in other words, the overflow flag is set to 1 if there is a carry from d6 to d7, or from d7 out. d7 out means d7 and the remainder would be on carry or another register, but not both. So only if one of them is happened. So again, if you have overflow in D6 and D7 together, in this case, V would be 0. It will not be converted to 1. Okay, nice. In example 13, the next example, sorry, the previous example, this is what we have already solved here. Because there is only a carry from D6 to D7, so this was our case. D6 was overflow, and D7 was normal without overflow. So in this case, we expect V equals 1. Nice. Let's see another example. Up till now, guys, we didn't solve the problem. So up till now, the N and the V flags are not sufficient to figure out if the number is positive or negative without errors or mistakes. So let's see this example here to see if we could solve the problem or not. So examine the following codes. Note that the rule of V and N flags we discussed in the previous slide. So LDI R20 with 80 hexadecimal and LDI R21 with FE. So this is R20, 80 hexadecimal, which is minus 128, and this is R21 with FE, so this is F, this is E, which is representing minus 2. How? You should get the 2's complement to figure it out how it is minus 2. And we could figure out before the 80 hexadecimal is minus 128. Okay, so now let's see together now if we added the two numbers together. So adding the two numbers together, we expect minus 128 minus 2, so it would be minus 130. This is in decimal values. So let's see what will happen here. When we add these two numbers together, the value would be like that, which means it's 7. And here we have E. So 7E is plus 126. So it's not minus 130. So this means the answer is wrong. So again, we cannot make this operation now, otherwise it would be wrong. Okay, so how can we figure out if it is wrong or not? Let's see again the values of flags. So here for the flag values, you have N equals 0 because the last number is 0. So this means it's positive number, it's not negative number. And because when we add bit number 7, we have one overflow. Let's figure out where is the overflow here in this addition. So 0, 1, 1, 1, 1, 1, 1, and 1 plus 1 equals 0, and we carry 1. So the overflow happened here because of D7. So V here should be 1. But we still have, guys, the error in our calculations. Our calculation is not right now. According to the CPU, the result is plus 126, which is wrong. And V equals 1 indicates that, note that N flag indicate that it is positive 126, and we have overflow. Note that N flag indicates the sign of computed result, which is here positive, and this is also not the right answer. So we still have the issue. How can we figure out if we have numerical error in our computation? So guys, we are going to conclude from the previous examples and find another solution to figure out how we can detect if our answer is right or not. But just let's investigate more about these problems, and we will figure out and solve all of these problems by another way. So let's see here this example. Examine the following code, noting the value of V and N again. So we have here LDI R20 with minus 2, So you can add by the way, this instruction is valid. So you can add the minus sign as negative number like that. So define the number like that is okay. So we have -2 and -5. When you represent -2 and -5 in two's complement, it would be like that. So 0, 1, 1, 1, 1, 1, 1, 1. So this is now the -2, and this is -5. When you add these numbers together, it should be -7, okay, or F9 hexadecimal. So this is when we add. Let's see the addition together here. So 0 plus 1 equals 1, 1 plus 1 equals 0, and we have carry 1. 1 plus 1 equals 0, and we have carry 1. 1 plus 1 equals 0, and we have carry 1, and plus 1 again, so we have 1, and we have carry 1. 1 plus 1 plus 1, so we have, sorry, let's repeat this again. 0 plus 1, 1 plus 1 equals 0, and we have 1. 1 plus 1 equals 0, and we have 1. 1 plus 1 equals 0, and we have carry 1, plus 1 again, so this would be 1. So I think we have also some numerical errors here, guys, for this part. So this is, we have overflow here, okay, and this is 1 plus 1 should be 1 plus 1 equals 0. Sorry, it's right. 1 plus 1 equals 0, okay, and we have carry 1, and we have 1 again, so this is 1. Again, triple 1, so we have 1 and carry 1. Triple 1, so we have 1 and carry 1. Triple 1, so we have 1, and should we have another carry here? So after making the addition together, we figure out that now we have overflow in both D6 and D7. Since we have overflow in both D6 and D7, this means our V is going to be 0, because we said V would be active high if we have overflow in either D6 or D7s, but both together, it would be active low. So here, V should be 0. And the carry flag should be 1, because we have 1 extra bit here. So carry flag in this case should be 1, but it's not required to write the carry flag here. What about N? Since D7 is active high, so we still have N equals 1. Okay, nice. So according to the CPU, the result is -7. So the result is okay. The result is okay. However, the flag is N equals 1 and V equals 0. We're still confused. So how can we figure out if this number is negative or positive? So N here equals 1, which reflects it's negative. But we could see previous examples, D7 may be 1 and N is 1, but still the result was positive. So let's see another example. In this example, LDI R20 with 7. Again, we need to figure out what's happening to N and V, overflow flag and sign or negative flag. So here you have LDI R20 with 7. So this is value of 7 now. Okay, 1, 1, 1, 0, and 0 is in the second nibble. R20 is 18. So 18 means 0, 1, and here you have 1. So this is now our 2 registers. Adding the 2 registers together. Sorry, guys, this is not 18. This should be 12. So there is a typo error in the textbook. I modified this in here in these highlighted numbers, but I forgot that one. So this number is not 18. As you can see, this is 2, not 8. Okay, so this is plus 12. So 7 plus 12, the answer should be 19. Okay, so seeing the answer together, 1 plus, now let's see that here, 1 plus 0 equals 1, 1 plus 1 equals 0, and we have carry 1, 1 plus 1 equals 0, and we have carry 1, 1 plus 0 equals 1, then 0 plus 1 equals 1, and then we have zeros, which means now our answer is 1 plus 8, which is 9, and this is 1. So our answer is plus 19. So negative flag here is 0 because the last or the most significant bit, D7, is active low, and V equals 0 because we don't have overflow between the 6th or 7th, D6 or D7. Nice. So we don't have any problem here in this example. Let's see now, guys, a solution how to figure out the negative sign of any computation and figure out if our solution is correct or not. So, as we mentioned before, the signed number, in signed number, any flag would be active high in D7. Okay, if the result is positive, the any flag would be 0, as we said. And if the result is negative, the any flag would be 1, which is why it's called negative. In operations on signed numbers, overflow is possible. Overflow corrupts the results. So the overflow can corrupt the result and negates the sign bit. It can damage the sign bit. Why? Because D7 would be 0, not 1. So if you add two positive numbers, in case of overflow, the N flag would be 1, showing that the result is negative, which is incorrect because there is overflow in D6. The S flag helps you to identify this issue. So the S flag helps you to know the sign of the real results. So now, guys, we can figure out the real result, not the error, by means of S. How can we find that? Let's see together how S is working. So S is checking the V flag in addition to the D7 bit. So S is going to check both V and D7, or we can say N, because N and D7 will be the same. Sorry. So what is the rule of S now? If V equals 0, so if we have V equals 0, it shows the overflow has not occurred, and the S flag will be the same as D7 to show the sign of the result. So in case of not having overflag, we don't have problem. In this case, N would be the real sign of our number. So this would be the same as D7 or N to show the sign of the result. But if V is active high, so this means you have overflow either from D6 or D7, it shows that the overflow has occurred. And the S flag would be the opposite of D7. So it will be the convert of N in this case, which means it's going to give you the real value or the real or corresponding to the sign of the real value. So we can finally say now S is the right flag that we can use to figure out if our answer or results is right or not, and the sign is positive or negative. Let's see a correction for all of the previous examples. So in example 13, guys, we had this operation here. So we added plus 96 to plus 70, and this was the result. The result was minus 90. So this is invalid because the result should be positive. So how S can solve this issue? Let's see here. Because the two positive numbers are added, the sign of the real result is positive. In this case, guys, you will find here S equals 0. So S equals 0 means our answer is positive. So in this answer, although we have N equals 1 and V equals 1 as well, okay, so we cannot get the right solution from N and V, so we can figure it out from S. So S here equals 0 means our answer should be positive, which means this minus 90 is invalid. Okay, so this number is positive. In example 14, because let's see firstly the example. So it was addition of minus 128 and minus 2. So the result should be minus 130. Okay, so here in this example, this was the result, guys. So the result was positive. However, we have negative numbers. Why it's positive? Because the last bit is active low. So it's invalid. How can we figure that it's invalid? This can be checked by means of S, because here n equals 0. And because we have overflow in the calculations in D6, okay, so V was 1. So here the S flag would be active 1. So S flag here will be active 1, and this is for negative. Okay, so the value of S flag is not the same as that of the N flag. So N here is not the right indication. So the indication is from S. In example 15, guys, we had this operation. So minus 2 plus minus 5 is minus 7 for F9 hexadecimal, and this answer was correct. Okay, but the overflow was 0, and the N flag was active high. So in this case, guys, N was active high, V was 0, and S was active low. So S indicates now the sign of our answer. So this number, F9, is not positive number. Why? Because it's coming from negative addition together. So this can be indicated from S. So S here can figure out the sign. In example 16, we had plus 7 plus 12. So the answer was plus 19. And the N flag was 0, which means the number was positive. And we had V equals 0. We don't have overflow. And the sign here is 0. S is 0. So finally, guys, we can figure out now if the number is positive or negative in any operation, addition, subtraction, any mathematical operation by means of S. So finally, if S equals 0, so this means we have positive number, and if S equals minus 1, so we have negative number. Sorry, guys. So now, guys, how can we check the flags? So we have some instructions to check these flags. We used some of these instructions before, but let's figure out the numbers or the instructions for the 3 bits we discussed today, which are S sign, N negative, or C carry. So in order to figure out these guys, we have the following instructions. So first instruction is branch if carry is set. So this is branching instruction. It would jump to a certain line if the carry flag is active high. And we have also another one for active low or clear. Okay, so we have this is for active high, and this is for active high, and this is for active low. This is active high, and this is active low. And for the V flag, we have also branch if V is carry, is C or cleared. So this is in case of active low. And here, branch of V is set, which is active high. Here also, for the S flag, So S flag is referred to here as PL and MI. PL means plus and MI means minus. So branch in case of plus, which means S equals 0, and branch in case of minus, which means S equals 1. Okay, so these are the instructions that you can use in programming to check if your results are positive or negative by means of these flags. So lastly, as a summary for the arithmetic operation, we could learn together in these topics, guys, this class and the previous class, the range of AVR unsigned data, the arithmetic operations for unsigned data. We discussed the addition, subtraction, multiplication, and division. The arithmetic operation for signed data, we discussed the how to deal with the signed data in addition, and the same is also would be for subtraction, and how the signed result must be checked by means of flags V, N, and S, and we said that the solution is in S to figure out if your number is signed or negative or not. So this was our class today. Next class, we will discuss some more advanced instructions related to microcontroller, like lookup tables, some other data or instructions which are going to be used a lot in our programming. And after that, we will have like 3 different topics: the interrupt, the timer and counters, and finally, the serial communication. Along with that, we will learn, guys, how can we use C language in all of these topics. Thank you so much, guys. Please, there will be office hour on Wednesday, on Thursday, and Friday. If you have any question regarding these classes, please don't hesitate to come to my office anytime or during office hour. Thank you so much, and see you in the next class.